Okay, let's come to a very central topic of theoretical physics. In general, the connection between symmetries and conserved quantities goes back to the German mathematician Emil Noether. She postulated more than 100 years ago that whenever you have a symmetry, and a symmetry, for example, is that um, your Lagrange function doesn't depend explicitly on the space coordinates. That means you can change space coordinates without your Lagrangian explicitly changing, only implicitly depending on this coordinates through other fields. Then you have, for example, translation symmetry. Yeah? You can move things around, push things around without the Lagrangian function changing. In general, whenever you have a symmetry, you have a conserved quantity associated to it. In daily life, we know, for example, angular momentum, things that are not invariant on the rotations, anything that can spin around and still look roughly the same. If you spin it up, it will keep spinning this way, and it would also um, try to keep its position in space in the sense that if you want to try to move it, like the bicycle wheel, to try to tilt it, it will resist this tilt because you are then trying to change the conserved quantity, and you have to apply force and do work in order to change that. So any symmetry nature nature has conserved quantity associated to it. It's quite a deep um, insight, and we looked at two possibilities or two realizations. One, so-called state space-time external symmetries. Yeah, so we don't have any specific dependence on space-time coordinates of the Lagrange function, for example. And then we can show the following. If we implement this variation with respect to um, external coordinates, it's just varying Lagrangian or with respect to x, y, z, and t, right? So we multiply it by derivative. We apply the derivative with respect to space-time, yeah, and then we raise the index to be contravariant with this metric tensor. That's what the variation here means. Now we write it out because we know that the Lagrangian depends on fields and derivatives of fields. You apply it in the chain rule, we get the first term where we take the derivative with respect to the field, then the derivative of the field itself with respect to space-time coordinates, and the second term where we have the derivative of the Lagrange density with respect to the derivative of the field, basically the generalized velocities, and then the derivative of those with respect to external space-time coordinates. This is the first step. Then we can use equation of motion on this term to replace the derivative with respect to the field by the derivative with respect to the generalized velocity and the derivative of it. Remember, we derived the general equation of motion up here, so we can replace this term by that term by setting those equal. So doing that on this term, we get this expression, and then we can apply the chain rule backwards, right? So we can pull out basically this derivative and write it as hitting this bracket here. So that would mean when I apply it to that first term, I get the derivative of this term times the derivative of phi, and I apply it to the second term, I get this term first here, and then this term derivative of hitting the other the derivative of the field again. So you have the two derivatives hitting the field. Okay, so you see that those and those lines are identical. So I apply the chain rule backwards. Now I see on the both sides of the equal sign this bit and this bit, and then I can set their difference equal to 0 by just rewriting this equality. right? And then I see since both have this derivatives hitting them, I can pull them out, and I have a quantity that is hit by derivative summed over this index and equal to 0. That means I can also defining this quantity here, this so-called energy momentum tensor, this will be, and I see that we see that this energy momentum tensor is conserved. That's called covariant conservation. Yeah. Um, Let me just briefly notice two things. One thing is it is connected to general relativity because a quantity that is related to energy and momentum that is conserved is really the only thing that you could use as a source for the gravitational field in general relativity, where we want to have a coordinate independent realization of the theory. In fact, I mean, you don't have to understand this equation, just bring it up here. The curvature, this structure here that is responsible for the curvature, is determined by the energy momentum tensor on the other side and is proportional to the Newton constant. That's the main equation of general relativity. So, and this is only possible because this is a conserved quantity, so it is an invariant, and we can safely use it as a source term for the gravitational field. Then I just wanted to mention here that the general continuity equation, yeah, can be rewritten as the bit that you have the derivative with respect to time of the first component, and you have the basically divergence of the current of the spatial current, and the sum is equal to 0. So that means if I take the integral, yeah, over this first component here, the spatial integral, I know that I can replace it by the integral over the divergence of this. I take the integral over the temporal component. I know that I can replace it by the divergence of the spatial current by setting those equal with the opposite sign. And as we discussed before, the integral over the divergence of the spatial current is just a boundary term. So you evaluate this current at the boundary. The boundary is infinitely far away, and we set to 0 the value of the current at the boundary. So that means this integral is 0. And that also means that the integral over the volume integral of the derivative of the time derivative of this 0 component is 0, which means that the volume integral of the over the temporal component is a constant. That means that this quantity is conserved. Yeah, right. So if we apply this to our energy momentum tensor that we just derived here, we know that it is covariantly conserved as per definition here. We then understand that this zeroth quantity, this in analogy to this vector like the representation in this zero entry quantity here is just the form momentum, and we know that it is covariantly we have derived from the basic principle of another theorem, and that this tensor is covariantly conserved, that this overall is a conserved quantity. The total form momentum of the field or of the theory is a conserved quantity. Furthermore, we know that checking the definition of T, we can verify that the 0, 0 component is just canonical momentum multiplying the time derivative of the field minus the Lagrangian. We can verify it explicitly by putting in the indices here, 0, 0. And we see that this is equal to the Hamilton function. So the energy momentum tensor is a tensor that has the energy in the 0, 0 component and the spatial momenta components and the diagonal components. And yeah, it's in general a covariantly conserved structure. That is here, and the fundamental conserved quantity that is induced by the invariance of the Lagrangian with respect to space-time translations. Well, they are not only external symmetries like space-time, like you can't just push things around in space, but also they are internal symmetries which we can't really affect ourselves, but they are nevertheless symmetries of the theory. And this is the case for the so-called charge. So there's electric charge, as you know, in nature, and it is called, in theory language, it's called U1 charge. Yeah, U1, just because you apply the simplest unitary transformation to it, as we just shortly discussed what it is, and then you find that this is the symmetry of the theory of your theory. Let us take the same Klein-Golden equation as above, except for the 1/2 normalization is now not needed because it's inside the definitions of the fields. The fields will be complex fields which have one component that is goes in straight away and the other is multiplied by the imaginary unit, and you have like the 1/2 square root normalization that would give you the analogous 1/2 normalization compared to the real case. Now we can see that we can now apply this unitary transformation, the simplest unitary transformation of the first order, the U1 transformation, so the transformed field phi prime is just e to the I epsilon, where epsilon is some parameter. Yeah, it's just multiplying it e to the I something, multiplying the field by it. And it's called unitary because we know that multiplying e to the I, or taking e to the I phi times its complex conjugate, which is e to the minus I epsilon, is just equal to 1. And this is the definition of a unitary transformation. So this is the simplest unitary transformation where this is just a number and not some other structure like a matrix. So we can also expand this e to the I epsilon as 1 plus I epsilon phi. This is the generator of this unitary transformation. And the complex conjugate is, of course, only has this minus I and hits the phi star field, and then you have 1 minus I epsilon phi star. Good. What happens if we plug this transformation in a Lagrangian? As before, we have the variation of phi. We use the variational equation, derivative of L with respect to phi, variation of phi, derivative of L with respect to the velocity, generalized velocity times variation of generalized velocity. And now we can again use the equation of motion to get the first term transformed in this way. And we again apply the chain rule backwards. You can verify that hitting this bracket with that derivative will give you back this expression here. So you see that the derivative of this quantity now is equals to 0, the total for derivative, which means that this is our conserved current. So now treating phi and phi star as independent fields, we can take this quantity and evaluate it for summing over phi and phi star. So the first term is that dl derivative with respect to the first field, phi, then with respect to the second field, phi star, we have two terms. We have defined what this variation of phi means. It's just multiplying them by I epsilon or minus I epsilon. Then we could pull out I epsilon and get a relative minus sign. So we have the variation of the Lagrangian times phi minus the variation of Lagrangian with respect to the conjugated field times the conjugated field. This will be our conserved current as per equations above. So we know that this current is covariantly conserved, and this is how it reads if we just take the Lagrangian above that we have here and plug it into this equation that we derived in the general form, plug it in. This will be actually part of the homework, and verify that this is the correct version of the current. Right? That means in the same way as I showed above, that the time derivative of the zeroth component, which is essentially um, the charge, is equal to the volume integral over this quantity is equal to the volume integral of over the spatial derivative divergence of this quantity. And we know that this is nothing else but the integral over the boundary. Let's say if we integrate over the space omega of all of the entire space, so this will be the boundary of omega. Let me write this as a boundary of omega term here, over a two-dimensional integral over j. Better to write it with a vector. Yeah? So you have a two-dimensional integral over the surface that surrounds this volume, and that is in general equal to 0. So yeah, so we know the time derivative. Well, let me write this 0 as explicit time dependence to make it absolutely clear. So the time derivative of this quantity that we can pull now outside, yeah. So the quantity is the volume integral of this charge. The time derivative of this is 0, yeah. So that's why we can conclude that the total volume integral of this quantity is a constant and it's a conserved value. So this is just the total electric charge. Well, I say electric, but in general it's a charge of this U1 symmetry, which in nature, for most practical purposes, can be called is the electrical charge. That's why electrical charges are conserved, because our symmetry, our theories respect this internal rotation symmetry, the U1 symmetry. All right. I think that should be enough for today, and I think this kind of last bit about the complex field should help you with the homeworks, and I'll see you next week.